All right, so this is a question that I brought up in the last video, and I want to actually do it now. So we've got this plane, and let's go ahead and first set up some axes. So I'm going to go ahead and call, I'm going to call this the y direction, and this the x direction. Come on. Oh, Apple Pencil, come on. Oh, there we go. All right, so this is the x direction, this is the y direction. The y direction is basically the same as north, and the x direction is the same as east. Right, so we're gonna put a coordinate system onto the sort of cardinal directions. Okay, so first thing, let's actually try to find the speed of the plane. So I know that the plane has an airspeed that is sort of that way. Actually, maybe more like that way. Right, and that is 200 meters per second, and at 30 degrees north of east, right, that basically tells me that sort of relative to this, right, that angle there is 30 degrees, right, because that's north of east means, like, if this is the east direction, it's 30 degrees towards the north from there, right, so this angle here would be 30 degrees. And there's also wind blowing, though, and the wind is blowing to the west. So the wind would look something like that. And now the total velocity, or the net velocity, would be that. Right, so let's call that v net, is that vector. Right, so we're doing the tip-to-tail sum of these two velocity vectors to get the total velocity of the plane, right? Because the plane basically moves 200 meters per second relative to the wind, but the wind itself is moving this way, right? Or I guess the plane moves at 200 meters per second through the air, but the air is moving because there's wind this way. So the total velocity of the plane, as seen from the ground, would actually look something like this, right? Where the length of this represents the speed, or the magnitude of the velocity, and the direction represents, this is the direction the plane's actually moving. So the plane is kind of pointed this way, but the plane is actually moving this way. And let's go ahead and label some of these, right? This is the velocity, the air speed of the plane. So maybe I'll just call that like V of the VP, and I'll call the speed of the wind VW. And VW is 40 meters per second. Okay, now we want to find v net, right, the net speed of the plane, and we want to do this first by finding what is this vector, and then we want to find the magnitude of that vector. So we want to add these two vectors, and we can't really get any information tip to tail because they're not scaled or anything, so I'm going to do it algebraically, but that means we need to find their components. So for v wind, it's actually pretty easy to write v wind in component form, right? V wind is just going to be equal to, has a negative x component of 40, and it has no y component. It's pretty straightforward. V plane is a little trickier, right? So let's go ahead and draw it out. We've got v plane x, v plane y. We know this angle is 30 degrees, and we know that the magnitude of v plane is 200. And I'm going to leave off the units because I don't want it to get too crowded. So here we can use trig to find v plane x and v plane y. So for v plane x, notice that this is sort of the adjacent side if we're thinking about this angle. So if we want to use adjacent and hypotenuse, right, adjacent, cosine, adjacent, and hypotenuse. So I know that cosine of 30 degrees should equal the adjacent side, VPX, over the hypotenuse, which is VP. So to solve for VPX, we could write it like this, VP times cosine 30, and that gives me 200 times cosine of 30, which is, I'll just do the whole thing. Cosine 30 is 0.866. It's like 173. right? I'll just go ahead and write that in right here. And it's meters per second. And then for VPY, right, this is the opposite side from here. So the opposite, and let's say we use the hypotenuse, opposite hypotenuse, so, right, sine of theta should be this over this, opposite over hypotenuse. So sine theta, let me go ahead and put in the angle, might as well. Sine of 30 degrees is equal to opposite, which is VPY, over hypotenuse, which is VP. So VPY is equal to VP sine 30, which means VPY. If I plug in 200 for VP, 200 times sine 30 is just 1/2. So this gives me 100 meters per second. And these should both be positive, right? Because this is in the positive x direction and this is in the positive y direction. So if I put these together in vector form, right, I get VP is equal to 173, comma 100 in meters per second. Right, and these are vectors. These are truly vectors, so I should use that sign. Now if I want to find the net velocity, if I want to find this vector, right, I simply add the components of these. So if I do that, this would give me negative, wait, no, not negative. This would give me 133, comma 100 meters per second. Right, so that's our V net. Cool. Now to find the speed, we want to take the magnitude of this vector, right? And sometimes I'll just write magnitude like this, right? Just kind of leave off that rather than doing those extra lines because it just gets kind of confusing. Right? Remember, to find the magnitude, we just use the Pythagorean theorem, right? Because this side squared plus this side squared should equal, oh, I guess actually we're looking, this is actually not this vector, right? This was this vector, but these are the x and y components of the total velocity vector. And to find the magnitude, we just have to use the square of each component or each leg, right? So if I were to draw this, I don't think I need to draw it, we're running out of space, but that's how we can find the length of that vector, right? One side squared plus the other side squared is equal to the hypotenuse squared. So that's why we take the square root. Now if I solve this, or if I do the calculation, I get something like 166 meters per second. Right, so that's the answer here. That's the speed of the plane relative to the ground. Okay, what angle does the plane travel at relative to the ground? So for this, I think I'm going to clear out some space. So this is a video, so you can always go back. No big deal. The angle of the plane. Let's push this back a little bit too. Okay, so if this is the net velocity, right there, and we also know, and I like to draw components with dotted lines, right, because it helps us remember that those are components of this vector, not separate vectors. Right, this is Vx, this is Vy. We're looking for this angle. Well, we have a few choices we could use here, right, because we know, right, we know V net x, we know V net y, and we know the magnitude of V net, right, so we really know all of these sides of the triangle. So I'm just going to use, I don't know, I'll use tangent, how about? So tan theta is opposite over adjacent, which would be the y component over the x component. So theta should be inverse tan Vy over Vx. So now, if I plug in the numbers, Vy is 100 and Vx is 133. So this is 100 over 133. So inverse tan of 100 over 133. And that gives me 37. So theta is equal to 37 degrees. Now, just let's process this for a minute. So originally, it says the plane is oriented, moving 30 degrees north of east, right? It's sort of moving this way. Now, if the wind is blowing to the west, right, it makes sense that the net velocity will look like this. So it makes sense we're getting an angle that's bigger than 30 degrees, right? Because this angle was 30 degrees. And if the wind is blowing this way, it makes sense that the plane will actually not move along this line. It will be pushed back a little bit. Right, so I'm just saying this answer kind of makes sense. Okay, what is the plane's displacement north in a time of 1 minute? Well, why don't we figure out the plane's displacement north as well as to the east? Because this is actually really important, and I kind of want to stress it. So if we want to find the plane's displacement north, we're actually looking to find a sort of a delta y, right? How far does it move in the y direction? Now, to find this, we have to think about just the plane's motion in that direction. And this velocity vector does just that, right? This tells me that the plane is moving at a speed of 133 meters per second this way and 100 meters per second that way. So if we want to think about the plane's motion just in the y direction, I could actually write an equation that looks something like this, right? V in the y direction is equal to displacement in y over time. So if I want to find how far it's traveled in the y direction, all I need to do is that. So Vy is 100, 1 minute, right, this is meters per second. Time is 60 seconds. So this comes out to be 6,000 meters. Right, so this is how far it's moved in the y direction in a time of 1 minute. We can do the same thing in the x direction, but we need to think separately also about motion in the x direction. Right, so we could do something like this. Right, this is literally how fast it's moving in the x direction. So if we want to figure out how far it goes in a given time in the x direction, we could think about it like this. All right, this is moving at a constant velocity. That's why we don't have to use kinematics equations or anything. So if I solve this for the x displacement, right, I get 133 meters per second times 60 seconds, and this gives me 7,980 is equal to delta x. So what this tells me is that in a time of 1 minute, this airplane will have traveled about 6,000 meters to the right, so 6 kilometers to the east, and about 8,000 meters or 8 kilometers to the north. Okay, so we saw that we can take vectors and we can add them with components, right? We looked at finding an angle related to a vector. We found the magnitude of a vector. And we even looked at the motion of this plane in the x and y directions. And this is going to relate to your next task, which is a sort of a simulation that I want you to look at. All right, so you might need to come back to this video to kind of help you out a bit. All right, I hope this was helpful.